Hello, welcome back to Abstract Algebra. In this video, I want to give you an introduction to the Sylow subgroups. Why are we interested in these groups to begin with? So just as a reminder, before we proved a big theorem, which is the classification of finite abelian groups, which was a theorem that says that every finite abelian group is isomorphic to a direct product of cyclic groups of prime power order. And to prove that theorem, we used some very fundamental things about finite abelian groups. First of all, we proved that if you have a prime and the prime divides the order of the group, then there is an element of order exactly p. What happens if we try to do that for non-abelian groups? We want to extend this theorem to non-abelian groups. So would the same proof work? Well, if you have a group that is non-abelian and P divides the order of the group, is this true? It turns out that yes, this is true actually for any finite group. And this is what's going to be what we call Cauchy's theorem. For any finite group, if P divides the order of the group, there is an element of order P, and that is Cauchy's theorem, which we are going to prove next in one of the next videos using group actions and the class equation. Okay. Second, in the proof of the case of finite abelian, we saw that if G is, if the order of G is a power of P times a number relatively prime to P, so this is the largest power of P that divides the order, then there is in fact a unique subgroup of G of order P to the K, of the largest possible P power order. In fact, the way we constructed that group was by defining what's the P primary component of the finite abelian group, and that was that group. And is that true when G is non-abelian? Well, it turns out that yes and no. Yes, there is a group. So there is a group in G of the largest possible size, but it is not unique. And I will show you an example in a moment. So there is more than one such group. So now we are already running into trouble if we want to recreate the same group theory proof for the finite abelian groups in the non-abelian group case. So it is not going to be so easy. And in fact, well, there isn't a classification per se of groups in the non-abelian case, but these tools might be useful in trying to classify at least some type of non-abelian groups. The last part that we used in the finite abelian case was the following. If G, the factorization of the order of G is these prime powers, then by 2, there are these groups with prime power order, which is the P primary components, and then we prove that G is direct product of all those groups. G is direct product of its P primary components in the finite abelian case. And is this true when G is not abelian? And that is the problem why this theorem or that structure of a proof doesn't work in the non-abelian case, is because no, even if we find these groups, groups that have that prime power order, the group itself in general is not going to be direct product of those because, for example, we'll take S3. In S3, we're going to have 2 subgroups. For example, 1, 2 is a group of order 2. The group generated by 1, 2, 3 is a group of order 3. And S3 is definitely not isomorphic to the direct product of these 2 groups because, simple reason, because this is abelian, this is abelian, so this would be abelian. This is in fact isomorphic to Z modulo X, which is abelian, and S3 is not abelian. So this part of the proof definitely fails, but we're going to try to see in what cases and under what circumstances we can recover things of this sort. Maybe not with direct products, with something that is called semi-direct products. In many cases, we can actually recover something of this sort using semi-direct products. And at any rate, knowing the existence of these very large groups of prime power order inside G gives us information that we can use in trying to classify certain types of groups. And we will see examples of that. So with that in mind, we define P-Sylow subgroups to be precisely when you have a group of finite order, a finite group, abelian or non-abelian, and the largest power of P that divides the order of G is P to the K, a subgroup that has that maximal order, maximal P power order, that's what we call a P-Sylow subgroup, or sometimes called a Sylow P subgroup. And then what we're going to prove is the following theorem. And we want to know, in this case, for example, we had uniqueness of a Sylow subgroup in the abelian case. In the non-abelian case, there might be more than one P-Sylow subgroup. So we want to know how to identify them, how many are there, and so on. So the Sylow theorems are going to tell us exactly how many are there. First of all, the first Sylow theorem tells you that there's always a P-Sylow subgroup. Those do exist. Two, that any two P-Sylow subgroups are related because they are actually conjugates. They're conjugate subgroups in G. And third, if you want to know what is the number of P-Sylow subgroups, then it tells us two things. The third Sylow theorem tells us that the number of P-Sylow subgroups is congruent to 1 modulo P, and the number of P-Sylows divides the order of the group. So it doesn't tell you exactly a formula for how many are there, but it gives you some sort of riddle that allows you in many cases to determine how many of them are there going to be. And once I know how many are there, then I can try to figure out, okay, what are they? So let me just give you some example of P-Sylow subgroups. So if I have a group of order 6, such as Z modulo 6, this is an abelian group, there's exactly one 2-Sylow subgroup, which is the subgroup generated by 3, so 3 modulo 6. And there is exactly one 3-Sylow subgroup, the subgroup generated by 2 modulo 6, so 2Z modulo 6Z. So this is an example of a 2-Sylow and a 3-Sylow subgroup of Z modulo 6. In S3, this is of order 6, and there will be 2-Sylows, non-trivial 2-Sylows, non-trivial 3-Sylows. And as I said, they are not unique anymore. This is a subgroup of order 2, so it is a 2-Sylow, but this is also, and that is also subgroups of order 2. So we have 3 2-Sylow subgroups, and we have exactly one 3-Sylow subgroup. So the fact that there is just exactly one in this case, that's something important, and we will see that if there's only one, then we know automatically that that subgroup is normal in the group. Okay, so I will stop here, and in the next video, we're going to start by proving Cauchy's theorem. I'm going to prove Cauchy's theorem, and then we're going to prove the first Sylow theorem, the existence of P-Sylow subgroups. And we will see that actually the proofs of Cauchy's theorem and the first Sylow theorem are very similar. So we'll start there. Until then, goodbye.